Okay, let's talk about the difference between static and kinetic friction. So, you may have noticed, possibly, that sometimes when you want to get something going, like if you had, say, a box sitting on a surface, and you started to push on this box, as you pushing, it's clearly not what someone pushing looks like, but you're applying a force in this direction, okay? You might find that you need to apply a fairly large force, but that once the box starts moving, the amount of force required to keep it moving is slightly less. Um, so what's going on, and why might that potentially, what might the potential cause of this be, right? So if this is the total force required to get it to start moving, then, you might only have this amount of force required to keep it moving, okay? So first of all, why is a force required to keep something moving when it's sitting on a surface? Because Newton's first law says when in motion stays in motion, right? What's going on here that, has you requiring a force to get something moving? Yeah, so what do we call this interaction between the bottom of the box and the surface? Right, friction. And if more force is required to get it going, and we realize that this force is essentially in response to friction, okay, uh, then there must be different friction, or different values for friction in this scenario where it's, starting out stopped, versus the scenario where it's, moving along. So we call this static friction, static of course meaning the friction associated with staying still, and kinetic or dynamic friction, depending who you ask. Okay? So two different kinds of friction. Um, Static friction is interesting. It's essentially reactionary, right? If I push a little bit, friction will accommodate me and push back equally. If I push a little bit more, same thing. Static friction gets larger. If I push a little bit more, static friction gets larger. If I push enough, I overcome static friction and I accelerate this thing and begin it, its motion. It'll start moving. Um, and this is different than kinetic friction, which I can, which I have to make be equal to, right? If I push with less than kinetic friction, I will accelerate negatively and this thing will come to a stop, right? If I push with larger than kinetic friction, I'll accelerate this because we'll have a net overall friction. Okay? So static friction, what do we call it? What do we call a force that changes in response to something? I think I might have just said it. Right. So this is a reactive force. Whereas, this is just, once you get it going, the kinetic friction essentially levels out at some value and it stays at that value. Okay? So non-reactive force. Um, we talked about earlier how to calculate for this, but we didn't really talk too much about the static part of things. So let's just recall how it is that we got this value. So we learned that the force of friction is equal to some mu value, which is a coefficient of friction, times whatever the normal force is. Okay. The IB way of writing this is slightly different. What they would say is they would say F D, meaning dynamic, and sorry, they actually use a small or a lowercase f. Let me just write it their way. I mean, it's semantics, but if you see it and you don't know what it is, it might make it tough. So F D, static friction, is equal to mu d times big R. Okay? So this is the symbol for normal. This is the coefficient of dynamic friction. And this is the force of friction. Okay, so this is the way that you would see this written from my probably. Okay, I think if you saw that, you'd probably be able to make the connection that this and this mean the same thing, right? Hopefully. And then similarly, force of static friction is also related to big R, to the normal. And something that you'll find is that the coefficient of static friction will always be larger than the coefficient of dynamic friction. Okay, there's a few things going on here. Okay, so at the kind of microscopic level, if we think about what's happening, okay, two surfaces are not completely smooth, right? So if we zoom in, what we're going to find is those rough surfaces, and if we further zoom in, we find that there's actually imperfections, mechanical imperfections between the two surfaces that make it difficult for these things to slide across one another, to make this slide across. And you can see that if there's a larger downward force, well, there's going to be a larger upward or normal force. And so the larger the weight of the object, right, the more firmly these two surfaces will be pushed together, and therefore the higher the friction will be. Hence, as R, or as the normal force goes up, the frictional force goes up, right? That makes sense. But the question is, why, once this is already moving, do you feel the mu value is lower than if it were sitting still to begin with? Why might that be? Okay, so it turns out there's not really a 100% agreed upon answer as to why static friction is larger than kinetic friction, but there's a couple of things that we can surmise, right? So let's imagine these two rough surfaces, sitting together, right? And they've sort of, if you want, settled together. Are you with me? So now if I start to push on here, let's think about the things that have to happen to get moving here, right? So I increase force, increase force, increase force, increase force in this direction, right? If this represents force. And eventually you're going to have this give, right? So think about what's actually going on. So you're pushing to the right, but look, you actually have to have a bit of a lift, right? In order for, say, this peak to get up and over the next peak, right? So there's got to be some lifting, number one. And number two, inertia has to be overcome as well, right? When something's sitting still, its tendency is to stay that way. So even if we had two perfectly smooth surfaces for a zero friction scenario, some force has to be applied to get that object moving, right? According to F equals ma. So there's also that. So you have to lift, number one, and you have to overcome inertia. Another thing that could be going on is that there could be unequal static charge here, okay? So if two objects that are dissimilar are put nearby each other, there can actually be a transfer of electrons from one to the other. So say like that. What that's going to do is it's going to leave behind a residual static electric positive charge here and a negative one here. So there's also the potential for some static electric pulling between the two objects, okay? Now think about that. That's going to require more force than just to have, if an object's already moving along a surface, well, that means it's kind of lifted up out of the pegs, and if it's already got some, inertia in and motion, it's going to tend to stay in motion, so it's not going to as easily kind of settle back into these cracks, okay? Now, whether this is exactly true or not is hard to say, but I think it makes logical sense if you think about it like that, okay? So there's a maximum value of static friction that you have to overcome, and once you've done so, all of a sudden the amount of force required drops back down as you, switch modes into the kinetic friction scenario or the dynamic friction scenario, okay? So hopefully that helps us understand that. Now, this is all measured out experimentally, right? You can't just say like, this surface will have this, value for its coefficient of friction. Someone has to actually go out and test that. It's not like, say, you know, how we could just use mathematics to figure out the acceleration due to gravity on another planet based on input parameters. You actually have to go out and measure, right? Now, you might have some standards set up somewhere that, for Teflon, for instance, at such and such a temperature with such and such another object on there, this is the coefficient of friction. We've figured that out, and that's been standardized. But as of right now, as far as I know, there's no real like true theory of friction that can predict that, what is the coefficient of friction between this type of rubber and, this type of asphalt at this temperature. There's not really a universal formula for that. Someone has to go figure that out. Okay? That makes sense? All right, sweet. That'd be